Web applications rely on a single, massive choke point to keep your data safe. Every time a user requests an action, a centralized authentication server has to cross-reference their identity against a master access control list. When millions of concurrent requests hit that server, it becomes a structural bottleneck and a highly lucrative target for attackers. Holochain discards this topology entirely. Because it is an agent-centric framework, there is no central authentication server, and there is no shared global ledger requiring network-wide consensus. Each node operates independently. But that structural independence introduces a specific risk. If any node on the network can directly route a message to any other node, the local state of every device becomes vulnerable to unwanted mutations. If there is no central authority verifying who is allowed to do what, how can an individual node prevent a malicious actor from triggering a function or extracting private data? To achieve peer-to-peer decentralization, those server-side access control lists have to be replaced. The security perimeter must move to the edge of the network itself, using a model known as Cryptographic Object Capability Security. Applications built on Holochain, called HAPS, are constructed from modular components called zomes. These zomes contain the business logic of the application, and agents interact with them by triggering a remote procedure known as a zome call. At the architectural level, a remote zome call is defined by a strict mathematical formula containing exactly 3 required variables. The first variable is ZF, the specific zome function targeted for execution. The second is params, the specific data or input parameters being passed into that function. The final variable is the capability token secret. This is an explicit permission token that grants the caller the exact authority needed to execute this specific action. By bundling the permission token directly inside the execution payload, the zome call becomes self-contained. The receiving node does not need to query an external database to verify the caller's intent. The proof of authorization arrives baked into the request itself. Before any peer can successfully transmit a zome call, an explicit permission relationship must be established and codified between the 2 nodes. This begins with the grantor. It generates a strict permission rule and writes it onto its local source chain as a capability grant entry. This entry tightly binds 3 elements: the function name, the allowed access level, and a randomly generated capability token. Once the grant is secured on the local chain, the grantor securely transmits this random token directly to the authorized remote peer, the caller. The caller receives the secret token and immediately commits it to their own local source chain as a capability claim entry. From that point forward, whenever the caller initiates a zone call targeting that specific function, their system will automatically fetch this stored claim entry to populate the capability token variable. Because these permissions are immutably logged on both local source chains, the authorization relationship is cryptographically auditable. 2 nodes can establish and enforce strict access control without relying on a shared global state. Traditional capability-based security ties authorization strictly to the possession of a bearer token. It functions like a physical API key or a movie ticket. The system grants access based on the presence of the data packet alone. A user clears a static security gate simply by presenting the token, which is completely independent of their actual identity. This creates a vulnerability. If that bearer token is intercepted in transit, the malicious actor who captures it immediately gains full access to the resource. The system only checks for the token, not the entity holding it. In a centralized system wrapped in SSL, that risk is manageable. But in an agent-centric peer-to-peer network, traffic routinely flows through untrusted intermediate routing nodes. In a zero-trust environment, merely possessing a secret token is insufficient. The underlying architecture must also rigorously verify the identity of the entity wielding that token. Holochain solves this by expanding the model into a 4-tiered access matrix, combining capability tokens with strict cryptographic identity verification. The first tier is unrestricted access. This functions like an open public API. It allows any node on the network to execute the function without needing to provide a capability token at all. The second tier is transferable access. This mirrors traditional capability security. A request will execute if and only if the caller can produce a valid capability token matching the grant. The third tier, assigned access, represents the highest level of external security. Assigned grants require the correct capability token, but also demand a digital signature from a specific public key. The request is subjected to a secondary cryptographic check before passing. The fourth and final tier is author access. Author grants are implicitly applied when the caller and the callee share the exact same public key. This allows internal component calls on a single device to bypass token checks entirely. The assigned tier effectively solves the bearer token flaw. By cryptographically tethering a specific network identity to a specific capability, a stolen token is rendered useless to anyone else. To see how rules are enforced, we examine the zome call execution context. Surrounding the core logic is the Holochain conductor. It immediately intercepts the request's provenance, the caller's cryptographic signature, and CN, the exact state of the receiver's local source chain. The Holochain conductor acts as a subconscious security system. It cross-references the inbound capability token and the caller's provenance against the original grant entry stored within that local chain snapshot. If those parameters do not align with the predefined rules, the conductor immediately drops the call. Malicious payloads never reach the application's core logic. The transport layer itself functions as a context-aware firewall, dropping requests before the zome code ever executes. Because this edge security model is robust, it allows agents to safely delegate their agency to other nodes and components on the network. This unlocks cross-DNA composability. Distinct distributed applications can interact with each other through precisely permissioned bridge calls and remote calls. Agents can exchange sensitive parameters and private data directly between their local source chains, passing information through encrypted peer-to-peer tunnels. In a public blockchain architecture, executing this kind of application interaction requires publishing state changes to a visible shared ledger. Holochain agents execute these interactions locally. The capability model guarantees data sovereignty. It allows for interoperability between applications while maintaining absolute privacy for the users. The cryptographic object capability model removes the need for centralized access control lists. By shifting access control entirely to the edge, distributed networks transform into highly resilient, zero-trust cryptographic ecosystems operating at scale. Every single function call on the network is mathematically provable, strictly permissioned, and inherently intentional. Security is maintained not by a central authority, but through cryptographic proofs verified against immutable local source chains. Holochain proves that a decentralized architecture can enforce strict authorization rules without relying on centralized bottlenecks or the heavy computational drag of global consensus mechanisms.